this video, I want to revisit something that I expressed in my mass moment of inertia video using an example problem. And in that video, I said that a general formulation for the mass moment of inertia is of the form I equals the integral r squared dm. So to do this, to look at how we make use of this equation, I want to look at this example. So in this example, I have a thin plate with a triangular cross section like this and some given dimensions, h and a. And I want to look at the mass moment of inertia for this object around the vertical axis, so around the y-axis. So I'm going to start with this basic formulation that it's equal to the integration of r squared dm. And I'm going to take this dm term, because integrating over the mass is kind of a confusing thing to think about. And I'm going to say, well, instead of dm, I'm going to write this as density times area. So now I'm integrating over the area, the cross-sectional shape. Now, I realize that density times area does not equal mass. Density, it needs to be multiplied by volume. But in our little planar 2D world here, we're going to pretend that we have a two-dimensional density such that we can multiply it by area to get mass. And from here, I'm going to say, well, I can also expand area, in this case, into my coordinate directions, dx and dy. So that's useful. I can see here kind of a double integration. Suppose I should throw an extra integration symbol in here. That's a bad looking one. And if I can evaluate that expression, then I can go ahead and figure out the answer to this problem. Now, the assumption we're making here is that density doesn't change. You can see I didn't put some, d rho expression in there, so we're assuming a constant uniform density, and that's necessary for this example. But I can go ahead and work through this from this starting point. All right, so to start evaluating this problem, I'm first going to rewrite my expression slightly. So I've said that I'm interested in rotation about the y-axis. And remember that this r value, which shows up as r squared in our equation, is distance, perpendicular distance from our rotational axis. So if I look over on my drawing, perpendicular distance, which would be r, is also equal to x. So it's measured in the x direction in this case. So that means that I can rewrite my integration, my double integration here, as x squared rho dx dy. And I want to kind of think about what's happening with my shape as I move across it, because I'm going to be integrating both in the y direction and in the x direction. So if we start down here at the origin, this bottom corner, and I move upwards with respect to y and to the right with respect to x, I want to think about my limits, because they're going to define my limits of integration. So first we can see that our triangular shape in the y direction is going to be ranging from 0 up to my height, which is h. So I can get a sense of what that is doing, and I'm going to treat y as my independent variable here. Now, as I move upwards and as I move over to the right, first I'm going to think about what is the slope of this line, because I have to be able to define how my x position changes as I move upwards in the y direction. So we know that slope is rise over run, and therefore I could write y equals rise h over a, which is the run, times x. But I'm actually going to reverse that. Well, first I'll write that this is rise over run. I'm going to reverse this and say that, well, x is going to be equal to a over h, y. So now I have an expression for x in terms of y. I know I'm reversing how I would normally write this, right? Usually we treat x as our independent variable. I'm reversing that a little bit here. And therefore, the limits for x are going to range from 0 to a over h y. So now, as y changes, so as I move up, my x position changes. And when, for example, y equals h, so I'm at the top, those h's in the equation cancel out right here. So y being h and this h would cancel out, and I'd be left with x equals a, which we know is true because at the top that's our dimension. So that allows us to define what's happening in terms of x and y for this expression. All right, so I'm going to bring those limits back over to my equation, and double integration like this would be evaluated, inside and outside. So the inside dx term means that my integration here has limits of 0 and a over hy. My dy term, so evaluating in terms of y, has limits of 0 to h. And I'm going to start then by evaluating the inside portion of that integral. So my inside portion, which is x squared rho dx, I'm evaluating effectively x squared with respect to x. So this gives me the integration in y, which hasn't gone away yet, I haven't actually evaluated that yet, of 1/3 x cubed rho evaluated between the limits 0 and a over h y. So now I can substitute in my limits. And my expression is now 1/3 a cubed over h cubed y cubed, which is going to be evaluated with respect to y. All right, so now we have to carry out the next integration. And I'm integrating with respect to y, so my non-constant term here is y cubed. So my integration is going to be 1/4 y to the 4th. 1/4 gets multiplied by 1/3 to get 1/12. And all of this is defined between my limits of 0 and h. All right, so finally I'm at a spot where I can kind of get rid of my variables here. I'm going to substitute in h for y, so that gives me h to the 4th over h to the 3rd. So all of those cancel except 1 in the numerator. And I get 1/12 a to the 3rd h rho. All right, so I'm getting pretty close. Recall that we defined rho as this kind of weird two-dimensional planar density. So with that, I'm going to say that rho is equal to mass over area. Our area in this case is just a triangle, and it has dimensions h and a, so I can write the area as 1/2 AH. Substituting this expression over in here for rho, and I end up with 1/6 a squared m. So I've got an expression now for this kind of arbitrary shape, which I maybe wasn't able to find an equation in the book. I'm able to evaluate that. And being aware that I'm using a few assumptions. I'm using uniform density assumption, and I'm assuming this 2D planar world. So this only really applies for a thin plate, right? If we have a thicker plate, then we need to do it in 3 dimensions, and it becomes a triple integration that we have to worry about. All right, thank you.